And so here, I might have given you an illusion that in the previous lecture, the two problems, one on the left with one point charge and conductor, is almost identical to the one on the right hand side with 2 point charges, one Q and one minus Q. But this might not be entirely true. If we look at the electric fields or to look at the scalar potential, indeed they are exactly the same on the plane, on the space uh, above this xy plane, but not everything are exactly the same. So one thing that I want to mention is if you calculate the total energy of these two configurations, they are slightly different. So the total energy has been derived before. So the expression goes like this. And here, this Qi is the ith point charge, and this V is the potential due to the other charge, or due to the other fields. And here, if we look at this expression, for the left hand side, this point charge here, Q, there is only one single point charge. And on the right hand side, there are actually 2 point charges. And so this means that the summation on the left goes only for one Q, and on the right, it goes to 2 Qs. And you can sort of imagine that the one on the right hand side should have twice the energy as the one on the left. And if that confuses you, then you can actually use the better way to understand. So remember that the energy can also be written down as the integral over E squared. I'm not remembering if there is a 1/2 in front or not, but the energy should be proportional to this the E squared over all space. And then this means that here on the left, we actually only have half of the space, because on the bottom is conductor and it's not the area of interest. And on the right hand side, and there are twice of any space. And this, the one on the E field on the up and E field on the below the plane should be a mirror symmetric one with, and this means that if you simply count the amount of the space the system has, the right hand side one should also be twice of the left hand side one. And if you do the integral, if you do the summation, the result should be Q over 2 and VI, which is, for a point charge, the VI is simply, and the distance is over 2D. So the final answer should be now. This can be checked by calculating the force and dragging the point charge from infinity to the position at the D here. And what's the force that the field due to the charge? So if we want to calculate the work, we need to calculate the force that we need to apply to the point charge when we are dragging the point charge from infinity to this D position, right? So this force should be the proportional to the negative of E. This is because we are interested in the calculating the force we need to apply to counter the electric field to bring that to the position. And here, what's the E field here represents? That's the E field that we calculated before by taking the negative gradient of V. Here the V is the here this V should be there are two terms, right? One term is the V that introduced by the charge on top, and another term is the the V introduced by the negative charge. So that's the V that we should use here. Or is there a different V that we need to use? So any guesses? Hmm? So when we are calculating the forces acting on a test charge, we always need to get rid of that test charge, right? So otherwise we are double counting the fields. So so here this B actually should not be the V that we obtained earlier. So it should be the V that's excluding the contribution of this above test charge. So which means that this V is really the V due to this minus Q charge. So this is the thing that you need to pay attention. And now this V is actually simple, only has one term, right? And the E field should also be a familiar point charge E field. So let's write this out. Here, because the V only has 1 over R, one term, then the corresponding E also has 1 over R squared, and it only has one term. And this R is really the spacing between the two imaginary, the image charge, the imaginary charge, and the original true charge. So here, this D spacing should be 2D. And now if we apply this, if we integrate this force, then that gives yeah, so here this force is the force experienced by the test charge, so the charge over here on top. So you can think that the problem is that this point charge will induce a certain amount of surface charge on the conductor, and then this conductor will have a feedback force applied to this charge of interest, and then this is the force that we are interested in. And yeah, sorry, this should be now if we integrate this, then this gives So, so you can check that indeed this agrees with what we obtained before. So, so this is the difference between the only difference between the image charge problem and this image charge with a conductor. Now the next question is how exactly shall we find the location of this image charge? So this problem in general is not an easy question to answer. So some intuition that we can get is we can actually use the optics to help us solve the problem. So here, remember that when we are calculating the point charge, we actually can think of this conductor as a mirror, and now this the image charge is really the mirror image of this positive test charge, except that when we are doing a mirror image, it's an inverted image, and here the charge should also take a minus sign. And there are also some restrictions that where you can apply, where you can put the image charge. You can never put the image charge back into the surface of interest, because say that you cannot put an image charge over here, because if you put a charge over there, you actually change the problem you are trying to solve. You can add charges everywhere outside of the surface of interest, and you can, but never put them inside. So this means that there are actually some limitations of where you can solve this problem. So not every problem can be solved by simply by using the technique of image charge. And you can actually see that it's possible to see a problem with two conductors. Say that one is, this is actually one of the homework problem, and I'm trying to plot one conductor over here on the left, and also one conductor on the bottom. So this is the xy plane, and this is the yz plane. And now you have two mirrors, and you can try to imagine that what you will see in the mirror. So you will see an image over here and also an image over here, but that might not be the end of the story. So because if you try to look at this problem, now you see that the image charge over here solves your problem on the xy plane, right? So that gives you potential 0. However, if you add another point charge over here, then this cures the problem at yz plane, but it introduces another problem at the xy plane. So you need to introduce an extra image charge to solve that inconsistency, and you can try to use your intuition from the optics, and maybe this one can simply do an extra mirror image somewhere, and then you can try to check in the end to see if your proposed image charge solution actually solves the problem or not by looking at the boundary conditions. So after you give out an expression for the potential, always check if they are satisfied at the boundary, and if they satisfy the boundary conditions, then you are done. And because you add what you added is outside the potential, outside the surface, and the inside the surface is the v introduced by this point charge. So the v should automatically satisfy the Poisson equation with a single point test charge in the region area of interest. and then if it satisfies the boundary condition, that has to be one of the solution, and that solution should be the one and the only one solution that you can find. And you might also see another problem as in that we have two mirrors, and then we have two conductors, and there is a point charge over here, and you can see that it's just like you standing in between two mirrors, and you can try to imagine where you will see yourself repeating itself. So you might, if you have problem figuring out what's the point charge distribution should look like, you can try to actually physically find two mirrors, and maybe in a salon, and to see how many you can find in the mirror. Okay, so let's now look at a slightly different mirror. Here in this case, there is actually a very special kind of mirror or conductor, is that we can try to solve the problem of a single test charge near a sphere that is grounded. So here this sphere is a 3D sphere, and for simplicity I try to plot a cut. So here I'm only showing the 2D geometry, but it can be really a 3D sphere. And now we want to, the idea of that is actually to generate an image charge somewhere such that the surface here of the sphere is an equipotential surface. Now this problem, where can we exactly put the test charge is the first step, right? So can we put somewhere around here? Can we put the test charge over here? So the problem is given a conductor with a sphere. So this is a closed sphere, and the outside over here there is a test charge. So we are trying to place image charge somewhere, right, to produce an equipotential surface of a sphere. So my first question is, can we place this somewhere here? Because naively thinking, right, you can think of this as a mirror, then this might be a probable location to put the charge. But can I put the charge over here? So do you know the reason? Yeah, so because this is the area of interest, we need to solve the problem here with no extra charge. So the only place to put a test charge is somewhere inside the sphere, and because we are not interested in the potential distribution inside, it can be any distribution. So now the next question is, where exactly do we put inside the sphere? So would you say that putting it here with a wise choice? Like so now we've allocated the position to put the point charge, right? So it has to be inside the sphere, but where exactly? So the inside the sphere there are many choices. So would you say that putting somewhere here is a good choice, or putting somewhere here might be a better choice? Yeah. So the reason why I think that putting it here might be a better choice is because take an extreme case. So think of this mirror, think of this conductor as a huge sphere, where the sphere is almost looks like this, like with an extremely large radius r. So in this, when this r is almost infinite, and if we put a point charge over here, then the test charge must be somewhere of distance d, right? So this is one of our intuition. And another intuition is that now we can take the point charge to be far away, where this point charge is actually somewhere around there. And now we can try to see where exactly do we need to put this test charge. It seems that if we put if this d is really infinite, then any test charge near this origin will make it equipotential, because this Q will have almost zero effect along this field over on the left. So now you get the idea that as you move this Q close to the surface, then the point charge should be somewhere around here. And as you move far away from this surface, it will move closer to the origin. And that is the some intuition that we can get. But exactly where we put this test charge, we need to do some mathematical derivation. So say that now the spacing here should be a, and we pick a distance. Let's claim this distance from the origin as b. And now if we are interested in the potential here, and there is one curly r1 and another curly r2. So what we want eventually is that say this is a q, this is q prime. So we want the potential produced as q over r2 plus q prime over curly r1. This expression should be a constant, or we can say that this is, if it's grounded, then it should be 0. So however, this point can change on this entire sphere, and now this means that the R1 and curly R1 and curly R2 can change, but because the charge here, Q and Q prime, has to be a fixed number. So if this really satisfies everywhere, then this means that this expression should be true, and then the R1, curly R1 and curly R2 should really be negative Q over Q prime. The ratio of the two should be a constant, right? So now, how mathematically can this be correct? So one way is to see that now if we specify this b at a magic location such that a times b equal to r squared, then that might happen, because now you see that there are two triangles. One triangle is RB gamma 1. Another triangle is R gamma 2A. And here, if this angle is the same, and if the ratio between this the ratio of b over r equal to r over a, then these two triangles are similar triangles. So this means that the ratio of So here A gamma 1 R and sorry, B gamma 1 R and R gamma 2 A. They should be all the same ratio, and this ratio should be the ratio of them should be A over R, right? So gamma 2 over gamma 1 is A over R. So if this is A over R, then automatically the R over B is also A over R, and that is guaranteed by AB equals R squared. So this is already satisfied. Now here this means that if we set the AB equal to R squared, and then these two will always have the same constant ratio, and because the angle of this is the same, then this is a similar triangle, then the gamma 1 and gamma 2 should also be always a constant ratio, that is A over R. And if that's the case, then V here should be always be 0. And so this means that indeed we really find out this ratio, and this ratio is also the ratio of Q minus Q over Q prime, which is A over R, which means here Q prime should be R over negative R over A times Q, and this is the point charge that we need to put, and the place B here and should be this means that now if we place the point image charge at a location of B equals R squared over A, and a negative charge, that is negative R over A Q, then this one will make the potential surface here at this radius R to be a constant, and this constant is actually 0. So you can see that to derive that mathematically, you really need to spend quite a few amount of time, and this is a problem that you might also see in the exam. So now you might see that if you really want to rederive this thing, it takes some time. And one possibility to derive that is to simply guess. Now I don't know the what the Q1 should be, Q prime should be, and what the B should be, but I know that what I want to make is the potential here at the surface should be 0 everywhere. Now we can actually, if we know this kind of solution exists, then we don't need to rederive that. We can simply pick up an arbitrary 2 point, and now if we have 2 points that satisfies V equals 0, then that supposedly should solve for Q prime and B. So what I mean is that now we can make a smart choice at simply to calculate the point over here and over there, right? Now this means that we try to calculate the potential at x equals R, and then this gives so here the first term is the potential due to the real charge, and because here this distance, let me try to plot another. So this is B minus, oh sorry, this is A minus R, and in between this is R minus B. So the second is the potential due to the imaginary charge, and we have the second possibility is that we can try to find out the potential at the negative R, which is similar. So here then this should be A plus R, and the other one should be R plus B. Now let's set both terms to be 0, and we can immediately solve for this question. So this means we multiply them to the denominator, Q plus Q prime A minus R should be 0 for the first equation, and for the second equation it should be R plus B Q plus Q prime times A plus R equals 0. Now if we add these two equations together, it gives us twice of RQ plus twice of Q prime A should be equal to 0. And if we subtract the second equation to the first equation, then it gives twice of BQ plus twice of RQ prime equal to 0. Now we have two equations, and two unknowns are Q and Q prime. So the first one can give us Q prime equals to negative R over AQ. Now if we put that into the second expression, then this means 2BQ plus minus 2R squared over AQ equals 0. Then this means that B should be an R squared over A. So this is how you can derive the coefficient of Q prime and B very quickly, but you simply already know the result and derive the Q prime and the B, right? It's not you prove that. So it, even though this is there is the Q prime and the B that you determine, it doesn't guarantee that at any other points this solution also works. And to prove that, you really need to go back to the mathematical argument. But this might be useful for you to quickly calculate what should the Q prime and the B are like in a short time. Okay, so in the homework you might also see the problem of really combine the effect of the spherical surface and plane surface. So this might be a conductor that has a radius of r, but it's also be connected with a plane conductor. But the idea is the same, that you can still try to use your imagination, try to simply test the region where you can put the point charge, imaginary charge. You can try to fix the surface for one, and then fix the surface for the other. And if you add a point charge that breaks the boundary condition, you can try to add another one to remedy that situation. And until you add enough point charge such that the final boundary condition is satisfied everywhere, then that is the solution that you're looking for. Okay, so next time we will talk about the separation of variables. It's a different technique, and this technique I think is much more powerful than the image charge technique. So I think that the image charge problem is really looking at some very particular problem that you can be guessed, and these cases are limited, and you cannot find every problem that can be. Most of the problem can actually not be solved by using this image charge technique, but using the separation of variables, you can actually solve a series of problems or many problems very systematically. So I think as a series you have to master how to use the separation of variables, because here this technique is also applicable in quantum mechanics, and if you try to solve a Schrödinger equation, say in 3 dimensions, you typically need to first separate the radius equation with the angular equation, and that might be helpful. Like it can reduce the dimensionality from 3D to 1D. So if you reduce that to 1D, then you are actually solving a differential equation instead of a partial differential equation. So that's the power of separation of variable. So for example, here we try to look for a 2D problem, and so it's still an ordinary differential equation, and it's still a partial differential equation. And what we want to solve for the boundary condition is there are no dependency on the z-axis, as you can see here. On the z-axis, that is the problem is independent of z, and what's dependent is on x and y. So really, if you want to write out the Laplacian, is now this problem we have to also specify the boundary condition. As you can see that there are 4 boundary conditions. The first one is the v at y equals a should be 0, and the v equal at y equals 0 should be also 0. And on the right hand side, if we go to x infinity, then the v should decay to 0, and that's the boundary condition at infinite, which is assumed boundary condition that we applied many times. And also this one particular boundary condition is a powerful boundary condition, is that the boundary condition on the left can be an arbitrary function of y. So for now we don't apply an explicit expression for v as a function of y, but we should assume that it can be really any function, and we don't plug in an actual example right now. And the problem to how we solve this problem is the following: that we first try to guess what the solution should be look like. Like we assume that the v can be written as the product of 2 independent solutions. That is, one is the solution that only depends on x, and another is the solution that only depends on y. Now let's see like if we can actually work this out. So we can plug this expression in, and here, because the partial derivative of x squared only applies to the v of x, then this actually can be pulled out. Let's see, use. Now let's move this v of y actually to the term over here, and then we can separate out the v of x and the v of y. Now the next is to actually see that here on the left it's an expression that only involves Vx, and on the right is an expression that only involves Vy. And for this to be satisfied, then the only possibility is that on the left hand side is a constant, because otherwise this can be, and on the right hand side is also a constant. Otherwise this function cannot be satisfied by every Vx and Vy. So here, say that if we really is possible to find the Vx now, if we are really possible to find out a constant such that these two expression is satisfied, then the above expression is satisfied, which means that by writing this v as the product of Vx and Vy, we actually separate this we separate this complicated partial differential equation, one single term, into two different expressions. And for one, we are only working in the x coordinate, and for the other one, we are only working in the y coordinate. And we can use everything that we learned in these ordinary differential equations, and that will help us solve the Vx. And we can also use the same idea to help us solve for the Vy. And now we simply need to, in the last step, combine the two solutions, and that will at least give us some possible solutions. Maybe that might not be the entire solution, because here we only have the solution only in terms of products of Vx and Vy. Now we can try to see if we can solve this problem. So along the Vx Vy direction, the right now we are still not sure if this c is a positive number or negative number, and say that c is a say that c is actually a positive number here for now. Then we express the c simply as a k squared, and then this means that along the y direction, here we can write out the answers immediately for this. So it should be either the sine ky or it can be cosine ky, and there is this coefficient c1 plus let's say this as a let's say this is C and D. So here I use again the same symbol as C, but here you should not be confused that this C is actually a constant, an arbitrary constant, and on the other hand, along the x direction, the answer should be slightly different, because for this y direction, it can be sine and cosine, because this c is a negative number, and because this coefficient in front is a negative number, but sines and cosines are not really the solutions for a positive quantity here. So instead of c, let's write as k squared. Now, the actual solutions could be actually exponential functions, and they could be an exponential of kx, or it can be minus exponential of kx, and that is and again, the solutions can be take any arbitrary linear combinations of the two. Now, this means that our final solution should really look like so for now we haven't determined what this ABCD should be, and we will try to determine this in the next lecture to see if we can use the boundary condition to fix the coefficient of ABCD. Okay, so the homeworks will be due Thursday for the homework 1.